Okay, welcome guys to everybody that joined us to the Groundwater Association of KZN, our third quarter, let's call it meeting, but with the current conditions, we decided to make it an open groundwater division webinar. Thank you very much for Yolanda from the groundwater division for allowing us to use their Zoom platform. Just a bit of background. Every year we, as a Groundwater Association of KwaZulu-Natal, we participate with the students in a career day, and also we try to assist them with sponsoring their Jubrai. Now, unfortunately, this year this can't happen, so we decided to invite two speakers from the university. Thank you for Prof. Mola that assisted us. And if I can introduce the speakers, I'm not going to talk too much. Let's start with what we're here for. Just a reminder, write your name in the chat box for the CPD points, and then please remember to keep your microphone on mute and your video must be off. So we've got two speakers from the University of KwaZulu-Natal. Manish will be the first presenter. He's going to talk about analysis of groundwater storage chains in the Usutu-Mhlatuze Drainage Region using GRACE satellite data. Manish is a hydrology PhD candidate from the University of KwaZulu-Natal. His current research interest involves the impact of land use change on surface water and groundwater resources in northern KwaZulu-Natal. And then we will maybe allow for one or two questions. And then our second speaker is Moreni. He's going to talk about the conceptual groundwater three-dimensional numerical model that he did for the Thyspunt area in the Eastern Cape. Moreni is a young professional hydrogeologist. He's a member of the Geological Society of South Africa and worked as a geologist at Marula Platinum Mine. He holds a BSc Honours degree in Geology from University of Limpopo and the MSc degree in Hydrogeology from the University of KwaZulu-Natal. So we will allow questions afterwards. We will limit the questions. And if there's any detailed questions afterwards, I'm sure Prof. Mola can supply more detail, but I don't have unfortunately the contact details, but I think through Yolanda we can arrange that in future. So I'm going to unshare my screen now, and please just another reminder to write in your name in the chat box. And for the CPD points, we're applying for a point 1 because we're going to be about an hour. And please remember to mute your microphones and stop your videos. Manish, I'm going to unshare now and you can fire away. Thank you, guys.
Thank you, Peter. Okay. Thank you, Peter, for the introduction, and also thanks to the hosts for giving me this opportunity to present my research work. As introduced by Peter, I'll be looking at the analysis of groundwater storage change in the Usutu-Mhlatuze Drainage Region using the GRACE satellite data. This is a part of my PhD work that I'm currently working on, and it's a work in progress at the moment. So just a brief background. Obviously, there's been an overuse of groundwater, which has caused a number of environmental problems, both locally and internationally. And the absence of sufficient in-situ groundwater monitoring networks, as well as the low-quality observation data, is a problem. And added to this, storage coefficients, which are used to translate this groundwater level changes to groundwater storage changes, are quite limited. The GRACE satellite product, however, has the potential to overcome this spatial and temporal challenge that is experienced by your traditional methods. So the aim of the research project that I'm working on is to assess the use of GRACE to determine the groundwater storage change in the Usutu-Mhlatuze water management area. So GRACE, which is the Gravity Recovery and Climate Experiment, was launched in April 2002 and ran until October 2017, and then it was decommissioned. However, following the success of that mission, the GRACE follow-on, also known as the GRACE Flow mission, was launched in 2019, and as a result, you'd see that there's a gap in the data between 2017 and 2019 when the satellite wasn't operational. So GRACE basically provides Earth observation data, and this data contributes to the understanding of your ocean mass distribution, your changes in your polar ice, your soil moisture information, as well as surface water and groundwater storage at large scales. Basically, GRACE operates using 2 satellites, which follow each other at a fixed distance of 220 kilometers. And on these satellites, there's this microwave ranging system. And this system is able to detect minute changes between these 2 satellites. And this information is then used to construct monthly maps of the Earth's average gravitational field. And this provides details on how mass, and mostly water, is moving on Earth. So as mentioned, GRACE provides terrestrial water storage. And your terrestrial water storage is basically made up of your soil moisture, your groundwater, and your surface water systems, such as your lakes, wetlands, rivers, and snow. And GRACE actually provides terrestrial water storage anomalies. And these are determined by taking the mean between 2004 and 2009 and subtracting that mean from each monthly value. And just to put it into perspective, so you have the addition of your groundwater storage, which you get from your in situ data, your surface water, and your soil moisture also coming from your in situ or hydrological models. And the addition of these 3 provide you with your terrestrial water storage. So looking at the application of GRACE to understand the water resources storage changes in the Usutu-Mhlatuze water management area. So the water management area, for majority of it, falls in northern KZN, with a small portion in Mpumalanga. And the water management area is approximately 270 kilometers wide in the east-west direction, and then 350 kilometers long in the north-south direction, which approximately equates to about 59,000 kilometers squared in area. It has a population of approximately 570,000 people, and some of the areas can be described as one of the most underdeveloped regions in South Africa. Unemployment, access to pipe water, lack of electricity, and low education levels, particularly in the northern eastern region, is quite prevalent. And the economic activity in the area ranges from subsistence agriculture, commercial agriculture. We have some quite a bit of commercial forestry, tourism, as well as some heavy industries located within the water management area. Looking at the climate of the region, on the screen we have two climate hydrometeorological data for stations located in the water management area. And generally the area is described as having a subtropical climate, and the majority of the rainfall occurs during the summer months between October and March, and is highly spatially and temporally variable. The mean precipitation ranges from 600 millimeters to 1,500 millimeters, and your mean daily temperature varies between 21 degrees Celsius to 32.1 degrees Celsius in summer, and 10.9 degrees Celsius to 26 degrees Celsius in winter. The area also experiences a mean potential evaporation rates of approximately 1,400 millimeters per year. Looking at the topography and drainage of the area, the highest elevation occurs as depicted on the map on your screen. It's approximately 2,200 meters, which is located in the western area of the study area. And then from there, it decreases gradually to sea level along the eastern coastline. An important fact to note is that majority of the large surface water bodies, so lakes, rivers, and wetlands, are found along the eastern shoreline, and these are predominantly groundwater driven. Included in this is Lake Sibaya, which is the largest freshwater lake in South Africa. Looking at the land cover of the area, what is quite outstanding is the commercial forestry, which is highly concentrated, or there's a high concentration of it in the northwestern areas of the study area, and as well as the coastline, particularly down below St. Lucia. And there's also a lot of agriculture present, your commercial and subsistence agriculture. And there's pockets of surface infrastructure, residential and villages scattered around the catchment, around the study area, with most of it concentrated in the northeastern area. The natural vegetation of the area is predominantly grasslands and wooded land. Looking at the hydrological setting, the northeastern coastal region of KwaZulu-Natal contains the largest primary aquifer in South Africa. And as mentioned, majority of these large surface water bodies are groundwater driven. And the groundwater in the greater water management area consists of, or occurs in three modes. And these are your intergranular or your primary aquifers, which mainly occurs on the coastal plain. And then you have your weathered and your fractured aquifers, which are found mainly inland. So looking at the methodology of the study, so the aim of the study is to find your groundwater storage change in the area. And there's two ways of doing this. One is the satellite-based method, and the other is your groundwater level or your in-situ data, using your in-situ data. And this is done by taking your groundwater level, multiplying it by storativity to get your groundwater storage change. For the purpose of this presentation, I'll be focusing on the GRACE application and using GRACE to determine your groundwater storage change. So as mentioned, GRACE provides you with your terrestrial water storage, and this data was downloaded from the Jet Propulsion Laboratory, and we used the latest release version, which is called the RL06 MASCON dataset, and this dataset has both the GRACE and GRACEFlow data. And this was downloaded from the launch date of the satellite, or from the launch date of the mission, which was in April 2002 up until February 2020, and this total to a total of 218 images. These are monthly images. The data was then processed, and the Coastal Resolution Improvement Filter, the CRI filter, was used, as this reduces signal leakage along the coastlines. Given that our study site was along the eastern coast, this had to be done. And then a gain factor was applied to the data set, which was recommended for hydrological studies. The surface data was obtained for 3 lakes and 9 dams. This data was obtained from the Department of Water and Sanitation for the same time period as the terrestrial water storage data from 2002 to 2020. 3 lakes at the surface water level data for the 3 lakes are the Causeway Lake, Lake Sibaya, and Lake St. Lucia, which is found right along the coast, on the eastern coastline. And then a total of 9 dams were also used. The soil moisture data was obtained from the Global Land Data Simulation, which was obtained from NASA, and this was monthly soil moisture data. And the data was downloaded to a spatial resolution of 0.25 degrees. And the data was produced using the NOAA land surface model, and was also obtained for the period between 2002 and February 2020. So earlier on, we had the equation showed how your TWS is equal to your surface water, groundwater, and soil moisture. So when we rearrange this equation, we look to find your groundwater storage. So basically taking your TWS, which is your terrestrial water storage from GRACE, minusing your soil water anomaly data and your soil moisture anomaly data. So the anomaly data was used because GRACE uses terrestrial storage water anomalies. So the mean between 2004 and 2009 for the surface water and soil moisture data was determined, and then this was subtracted from the monthly data. Looking at the results in discussion, the graph in front of you is the GRACE-derived terrestrial water storage for the entire Usutu-Mhlatuze water management area. And you look at the trend from 2002 to around 2006, there was a decrease in your TWS data. And then from then all the way up to 2016, there was a gradual increase. Obviously, there's some variation. And what's quite noticeable is from 2017 to current, there's just been a very steep decline. The area between 2017 and 2018 is the gap in data as a result of the satellite not being operational. And then the gaps that you see from 2002 up until 2017, those gaps are as a result of obviously satellite maintenance or cloud cover. So when there's cloud cover, satellites can't pick up any images of the Earth, which was quite a big negative point using satellite data. The soil moisture data that was derived from the Global Land Data Simulation system is projected in front of you, and this is also for the entire water management area. And generally, the trend is quite consistent, especially between 2004 and 2013. We see that the soil moisture ranged between 0.8 centimeters and 0.8 centimeters from the anomaly. And what was quite noticeable is between 2014 and 2020, the range decreased. The maximum was 0.5 centimeters, and the minimum went down to 0.9 centimeters. So for the purpose of the study site was divided into primary aquifer and the secondary aquifer, based on its hydrological characteristics, such as the storativity. And it was a very similar trend to the groundwater storage change for the entire catchment. There's a general increase that we see from 2004 to 2014, and then a very steep decline all the way to 2020. And generally, the groundwater storage change increased by 7.64 centimeters in March 2014. That was the highest it went. and then it decreased by 15.3 centimeters in November 2019. And between the operational period of the satellite, well, from 2002 till current, there was a total decrease in groundwater storage by 636 million cubic meters for the primary aquifer. For the secondary aquifer, we see the same trend once again, consistent with the trend of the entire study site as well as the primary aquifer. However, the maximum storage increase changed by a deviation from the mean was 8.72, and the groundwater storage change decrease from the mean was 12.66 centimeters in November 2019. However, the groundwater storage change between 2002 and 2020 was much more, which is a decrease of 2,400 million meters cubed. Excuse me. And the reason for this big difference was related to the size of the secondary aquifer compared to the primary aquifer. So clearly, there's a decreasing trend in groundwater storage from the GRACE data for both the primary and secondary aquifers, as well as the entire study area. And in particular, the last 5 years have seen a significant decrease in groundwater storage in the area, and this may pose a threat to the environment. What I did was I had a look at some in situ data that I had available. This is so the graph on the top is your groundwater monitored data between 2002 and 2020 from selected stations located in the primary aquifer. This data was obtained from the Department of Water and Sanitation. And looking at this data, you see there's a decrease from 2003 down to late 2005. We have an increase again, decrease, but what's noticeable is the decrease from 2012 to 2016. And if you compare that with the GRACE-derived storage, groundwater storage for the primary aquifer, we see quite a similar trend as well. We see that particularly looking at the last 5 years, 5-6 years, the groundwater levels have decreased, and this is consistent with the GRACE graph at the bottom as well. From 2015, we see the groundwater levels decreasing during that period as well. A similar comparison was done for the secondary aquifer. So the graph on the top, we have your groundwater monitoring data from 2002 to 2020 for selected stations in the secondary aquifer, and the graph below is your GRACE-derived groundwater storage for the primary aquifer. And similar trends were seen. The decrease, focusing on the last 5 years where there's been a major decrease, we see that also from 2014, 2015, or well, from let's say late 2013, moving forward, the groundwater level data has been in a decreasing trend, and this is consistent with GRACE. In 2015, moving forward, there has been no much positive movement for groundwater storage has been declining. So studies have highlighted that the change in climate and land use may be a contributing factor to this decrease in groundwater levels. Global Indemnity 2018 highlighted that a decrease in groundwater levels as a response to prolonged reduction in rainfall. And in particular, the Usutu-Mhlatuze water management area experienced a decrease in rainfall and groundwater levels between 2002 and 2016. And looking at land use, a number of studies highlighted that the establishment of commercial forestry and eucalyptus and recent groundwater pumping trends have accelerated the decline in groundwater levels at the site. Looking at the coastal plain, particularly in northeastern KZN, commercial forestry has increased by over 1,000 hectares per year since 2002. And studies have revealed that commercial forestry was a cause of a 35% drop in water levels of Lake Sabaya, and that the removal of forests from the catchment would increase water yield substantially. And this is relevant given that the lakes or surface water bodies in this area is interconnected with the groundwater. In conclusion, the study area, particularly the coastal regions, experienced a drastic decrease in groundwater storage. Between 2002 and 2020, the primary aquifer experienced a loss of 636 million cubic meters. And during the same period, the secondary aquifer experienced a loss of 2,400 million cubic meters. And this is due to the limited groundwater monitoring stations and the low quality data. They have a very limited spatial representation of groundwater storage, given that they're point-based data. And they make it very difficult to calibrate the GRACE anomaly. And however, in areas where the data is limited, or limited groundwater monitoring stations, GRACE has the potential to bridge this gap. Finally, I'd just like to acknowledge my supervisors, Prof. Mola Demi and Dr. Michelle Tosha, and as well as my funders, FTR and Sayan and the NRF. Thank you.
Thank you very much, Manish. That was very interesting. I don't know if there's any questions now. Maybe put your questions in the chat box and we can address them at the end of the second presentation. I can't see any questions. Yeah, and please, just a reminder, if everybody can write their names in the chat box for the CPD points. And thank you for muting your mics and your videos. I think, yeah, let's go over to Moreni. If you can share your screen, you can fire away with your presentation, and then we will have a couple of questions afterwards for both Manish and Moreni. Thanks.
Afternoon, ladies and gentlemen. My name is Mr Modiba from University of KwaZulu-Natal. Today, I'll be presenting the three-dimensional numerical groundwater flow and advective transport modeling of the Thyspunt area in the Eastern Cape, South Africa. Here is the content of my presentation from the background of the research, aims and objectives, down to the conclusion and recommendations. The Thyspunt area is selected for a future nuclear power station. So as part of the environmental impact assessment, a detailed conceptual hydrological and a numerical groundwater flow and a transport model are required. So in this research, it involves the understanding of the prevailing hydrological condition through a three-dimensional numerical groundwater flow modeling. So to achieve that, a conceptual hydrological model is an important aspect of the development of a groundwater flow and contaminant transport model. So a robust conceptual hydrological model relies on a detailed hydrological characterization, which include analysis of pumping test, groundwater occurrence, storage, flow, and hydrochemical and environmental isotope analysis. So the aims and objectives of my research are as follows. The main aim of this study is to understand the groundwater occurrence, storage, flow and its interaction with surface water system through a conceptual hydrological and numerical groundwater flow modeling. And the specific objectives of the research are to develop a conceptual hydrological model, to calibrate a 3-dimensional groundwater flow model, to study the advective transport of contaminants within the study area. So the study area is located in Eastern Cape, South Africa. It's approximately 120 kilometers west of the town of Port Elizabeth, and it's approximately plus or minus 700 kilometers east of Cape Town. The study area has a subtropical climate with year-round rainfall, mainly influenced by the southerly temperature moisture. As we can see, the study area receives high rainfall during winter period, and the main annual precipitation is around 622 millimeters per annum. Figure 3 presented the topography of the study area. You can see that the highest elevation around the study area is 222 meters above main sea level. And then we have 2 major drainage systems, namely the Crom River and the Klipdrift River, which are draining water from the highlands into the Indian Ocean. The main lithological units in the study area are made up of the Cape Supergroup and the Algua Group meta-sedimentary rock. The study area is known for its complex geology caused by a ductile deformation as a result of a northerly directed intercontinental compression associated with the Permo-Triassic Cape origin. And we see that the study area, the Table Mountain constitute most of the base of the geology in the study area. Figure 6 shows the cross-section and the geology across the study area. We can see that the TMG is highly fractured, and these are some of the boreholes which are drilled in around the vicinity of the study area. And here is just to show some of the on figure 7, it shows some of the outcrops within the study area. You can see how the quartzite are highly fractured, which shows that the fractures shows the preferential pathways for groundwater. The hydrogeological setting for the study area, we managed to identify 2 types of aquifers. We have the intergranular aquifer, which have a potential to yield over 0.5 liters per second, and we have the fractured aquifer, which are part of the Table Mountain group, which yield around about 0.5 to 2 liters per second. This aquifer, the intergranular, the fractured aquifer, are less productive as compared to the intergranular aquifers. Here is to show the methodology and approach that we took during the course of the study. We collected climate data. This climate data includes the meteorological data, the rainfall, temperature, wind speed, and solar radiation, and etc. And then we also interpreted the topography and the drainage from the study area. So based on the geological model and the aquifer characterization and the groundwater recharge, we managed to develop a hydrostratigraphic unit. And we also analyzed the hydrochemical characteristics of the study area, where we analyzed for major ions and trace elements, and also integrated the isotopic information into the conceptual model. So all this information helped to develop a robust conceptual hydrological model, of which was later converted into a 3-dimensional numerical groundwater flow model. And a well-calibrated 3-dimensional numerical groundwater flow model was then converted into develop an advective transport model. Here is to show the locality where we took our samples. We took soil samples, rock samples, and surface water samples, and also groundwater samples from the study area. The results and discussion. On table 1, it shows the statistical summary of hydraulic parameters of our 2 aquifers, which are the Alqua group and the Table Mountain aquifer. So here we analyzed for the transmissivity, the hydraulic conductivity, specific yield, and also the storage, which we assisted us into developing a numerical model. On figure 12, note the ion oxidation precipitation. This occurred on one of the artesian boreholes on the study area. Figure 13 and 14, they present the depths to groundwater and groundwater flow direction within the study area. We can see that the local groundwater flow direction is complex due to some rivers and dams within the model domain, but the general groundwater flow direction is towards the Indian Ocean. The groundwater recharge was estimated using the water level fluctuation method, and the weighted aerial weighted recharge is around 40 milliliters per annum. The physiochemical characteristics of the aquifers, the groundwater and surface water indicates a circum neutral pH condition with a mean pH of 7.3 and 7.6, and the main EC is 1,103 microsiemens per centimeter and 1,730.86 microsiemens per centimeter respectively. So on figure 16, we can see the EC distribution across the study area. So the groundwater from the study area is classified as freshwater. The hydrochemical characteristics of study area, we see that the alpha group are dominated by calcium magnesium bicarbonate hydrophysis, and we can see on the Piper diagram we have an evolution of freshwater on the Piper diagram, of which is also supported by the Duroff diagram, on where we see that most of our sample plot along the dissolution line or the mixing line. And we also use the Schweller diagram just to illustrate the abundance of major ions in groundwater within the study area. We also did analyze the environmental isotopes. With the environmental isotopes, we see that most of the groundwater within the study area, it's plot along the meteoric water line, and the groundwater samples, rain samples, and the majority of spring samples, they plot in the condensation field due to lack of evaporation. And then some of the seawater and surface water, they plot on the evaporation field, indicating the impact of evaporation. We also did the tritium analysis. The results show that 2 types of aquifer are, the water is modern, with the tritium around 1.5 to 3.1 tritium unit, and the older water, which are circulating at the deeper TMG aquifer, they are less than 1.0 tritium unit. So with all that information, the geology, the hydrochemistry, the environmental isotope, we managed to develop a conceptual model, and also including the depth to groundwater level and also the flow direction. So the robust conceptual hydrological model was converted into a 3-dimensional groundwater flow model. The software used for modeling the groundwater flow system of the Thyspunt area is Moodflow within the GMS graphic user interface. And all inputs parameters were prepared using ArcGIS. And the Moodflow NWT, or a Newton formulation for Moodflow 2005, that uses the UPW upstream waiting flow package, and NWT Newton solver was also used. So the model was divided into two layers. The upper layer, or the upper model layer, was made up of the unconsolidated alpha group formation, and the bottom model layer was made up of the Table Mountain group formations. And the lowermost boundary of the model is estimated using the deepest borehole from the study area, and it was assigned a constant elevation. Figure 20, it shows the boundary conditions within the model domain, or around the model domain. And along the coastal line, we assigned this coastal line a specified head boundary condition, which is the first type. And then on the northern part of the study area, or the modern domain, we assigned a non-flow boundary condition, which is the second type, or the Newman boundary condition. And then the rivers were modeled, or were assigned, a constant head boundary condition. And the streams within, or the stream inside the model domain, were modeled as drains, and the pond and dams inside the model domain were given a general head boundary condition. So the horizontal extent of the model is designed as 26 kilometers by 36 kilometers, and the area was discretized to a regular model grid of 384 rows and 651 columns, corresponding to a cell size of 30 meters in both X and Y direction. So the initial condition was set as follows. The top elevation was used as the starting head condition for a steady state simulation, so that the model can converge successfully. The model calibration, the steady state model is calibrated using a trial error automation calibration test, following the calibration criteria: the mean error, the mean absolute error, the root mean square, and the coefficient of determination. So we can see on table 2 that the calibration error, especially on the mean error, it's negative 0.41, which is close to 0, and even the other errors, they are very minimum. And we see again the plot of computed versus observed head for steady state. It shows a good fit with the regression coefficient of 0.95. And we further evaluated the steady state calibration using the water budget for the model domain. We can see that the total inflow, as we subtracted from the total outflow, that the result or the value is close to 0, which shows that the model was successfully modeled. And even the percentage difference, it's almost close to 0. And on figure 22, we are illustrating the contour map of simulated groundwater head distribution with the associated error bars. And on figure 23, we present the relationship between observed head and the model simulated head at each piezometer. We can see that the trend, it's similar of the observed head and the simulated head, which shows a good fit. The transient model was also calibrated using similar calibration criteria as the steady state model. We can still see again on the error values that they are very small and they are close to zero. And even the scatter plot of computed versus observed head for transient model shows a good fit with the regression coefficient of 0.995. So we further checked each piezometer if it was well calibrated, and the results are presented. This is one of the piezometer which was checked if the calibration went well, and we can see we can see that the simulation is transient. And also here is another piezometer which shows a good fit between the simulated head and the observed head. And also on figure 26B, we can still see the trends shows a good fit. And even here is some of another piezometer. We did the same thing as the previous piezometer. And here is another piezometer where we also checked. And then from a well-calibrated steady state model and a well-calibrated transient model using a statistical error criteria, we now conclude that our model was well calibrated, and now it's ready to be used for a particle tracking scheme. So the forward particle tracking scheme was used to investigate the potential flow path and particle velocity. And these particles were injected at the center of the proposed site for nuclear power station. So we can see that after a year, it shows how the particle migrated. As the years increase, we can see that the particles are moving towards the Indian Ocean. And the average groundwater velocity is about 0.16 meters per day towards the Indian Ocean. And we continue tracking the particle for the next 100 years. We can see how the particle move within the proposed nuclear power plant footprint. And we also run the reverse particle tracking exercise, which indicates no threat of seawater intrusion along the coastal into the model domain. We can see that we don't have any seawater intrusion coming into our model domain. In conclusion, a robust conceptual hydrological model of the Thyspunt area was successfully used to calibrate a numerical groundwater flow model. And the three-dimensional numerical model has been calibrated under a steady state and transient condition. And the results of the calibrated model were evaluated against statistical error criteria, including mean error, mean absolute error, and the mean root square, and also the regression coefficient. The calibrated numerical model is used to understand the advective transport of the hypothetical conservative contaminants released at the proposed footprint area. And the results of this forward particle tracking indicate that the contaminants need over 4 decades to reach the Indian Ocean. So one of the recommendations is that continuous groundwater level monitor is required within and in the vicinity of the proposed model domain to validate the calibrated result, the calibrated numerical model. Yeah, some of the sources we used during this research. And I would like to thank Prof. Demli and Prof. Tamuru for supervising the project. And I would also like to thank the National Nuclear Regulator for funding the project. And I would also like to thank the Groundwater Division and GAKZN to giving us this platform to present our research. Thank you.
Thank you, Mary. I see there's two questions. The first one is for Manish. Thanks, Manish. Would like to please find out if there is any correlation with the lack of flood releases from the Pongolapoort Dam, in brackets, false numerous pans, and groundwater recharge, probably focusing on the secondary aquifer. Not sure if you understand that. It's in the chat box, the third one, or fourth one from the bottom. Manish, if you can maybe comment on that. Just remember you unmute yourself.
Okay, thanks, Shivashni, for the question. I haven't looked into that, but it would be something to look into. It would be quite interesting to see if there is any correlation. And I'm sure with the data that I have, I could probably be able to look into that. And I will let you know if I find anything on that. Thank you.
Thanks, Manish. And then from Peter Roseborn, just maybe a couple of comments. Prof. Mola already answered the last one. In terms of your no-flow boundary in the northwest there, conceptually recharge is postulated flow from the higher lying TMGA of the Carredo mountain towards Cape St. Francis. Therefore, not sure about the no-flow boundary across this area. Remember, I think that's, if you want to comment on that, the first part of the question.
I think the reason we assigned a no-flow boundary from that area, we wanted that that area, we don't have what do you call, we don't have rivers or what we call this, a groundwater divide at the site. So that's why we assigned that area as a non-flow boundary condition, not to allow water into the model domain.
Okay, and then the second part of the question is, how were the aquifer parameters such as TNS values derived? From test pumping or from previous work?
They were derived from pumping tests. We had data from the NNR, and yes, they were derived from the pumping test.
Okay, so you received the data that was already conducted in the field.
Yes.
And then just on, will you consider doing advective transport from the proposed nuclear installation footprint in future, or was that, I suppose it was not done?
Sorry, can you repeat the question again?
Yeah, it's the last part there. I'm just going to read. Why not do advective transport from the proposed nuclear installation footprint?
Yes, we did the advective transport also on the footprint.
Okay, so you just didn't include it in your presentation?
Yes, we didn't include it on the presentation.
Okay, no, that's great. I don't see any other questions, and I think it's fair to conclude. Thank you for everybody on behalf of the Groundwater Association of KwaZulu-Natal. And just for the latecomers, we usually have a student session in our association where we do career days and sponsor their Jubra. So that was the reason we involved Manish and Moneri. Thank you very much, guys. I appreciate your time, and it was very interesting to share your information with us. And then Prof. Mola, thank you very much from your side, and from the Groundwater Division, Yolanda, for helping us doing this platform. And please remember to write your name in the chat box. We will distribute CPD certificates to point 1, but it all adds up. If there's nothing else, then yeah, thanks a lot, and We see each other soon. Thank you.